Hello, welcome to this presentation for the early universe from home. So I'm going to be talking about the first trillionth of a second after the Big Bang. And someone should write a book called this if they haven't done it already. But the first trillionth of a second is obviously the modern version of the first 3 minutes, which in 1975 it was radical enough that Weinberg was able to take the then recent discovery of the microwave background and the fact that the temperature of the universe was around 3 kelvins, and use that to discuss the physical processes that we could be reasonably certain then took place minutes after the Big Bang. But our focus is going to be the first trillionth of a second. And as the universe gets hotter, as we go back in time, uh, minutes after the Big Bang, it's at MeV scales, but a trillionth of a second after the Big Bang, the universe is hot enough such that typical interactions are happening at TeV scales and obviously above. And so the first trillionth of a second is different from all the other trillionths of a second that happened since the Big Bang. And that's the only trillionth of a second where we don't feel that we have a reasonable handle on the fundamental laws of physics that apply during that period. And once you get into the range of accessibility for the TV, for the LHC rather, we know that energies are typically going to be sub-TeV. And in that region, obviously, the standard model is going to hold reasonably well. So we're living in a domain where both the laws of physics and contents and behavior of the universe are obviously up for grabs. So in particular, whenever we're thinking about cosmology, we're obviously thinking about a whole range of different timescales. And so we're going to be looking at the post-inflationary universe. But the clock that ticks, the two clocks that tick post-inflation, one of those is a clock that is controlled by the dynamics of the scalar field itself. And that can be a very speedy tick indeed. The other clock is one that's controlled by the expansion of the universe, so the Hubble time. And those numbers are going to diverge. The numbers that are controlled by field theory will stay relatively constant as the universe expands. But numbers that are associated with the expansion of the universe, obviously that process slows down once we get outside of the inflationary phase itself. So most of what we're going to need to talk about today, in fact, pretty much everything we're going to need to talk about today is buried in the single scalar field that we write down its equation of motion in its full form, where the box operator is the generalized wave equation written down relative to the appropriate space-time metric that we're thinking about. So if we assume a homogeneous and isotropic space-time, so only time dependence, it's been known since the 1920s that leads to a universe that has dynamics that look very much like the Big Bang. But when we make that assumption, of course, we're dropping the spatial derivatives out of our wave equation, and we come up with the usual equation that governs evolving scalar field and inflationary dynamics. So we're interested in the time after inflation, and so we know that inflation ends in simple models when slow roll breaks. And on top of that, constraints on R, the ratio of the amplitude of the tensor or potential tensor perturbation background relative to the scalar or the density perturbation background. We now know that that's less than about 0.036. And so that's telling us that when we look into the dynamics of slow roll, that's telling us that phi at large values of the values of phi where we think inflation would be happening can be growing at a rate like phi to the p. But p, if we're going to write this down as a single potential with a single term, has to be less than 1. So in other words, it has to be something that's growing relatively slowly. So the small field limit, the limit of the inflationary dynamics once inflation has come to an end, has complex dynamics. So after inflation, it's a requirement, and this is something that's been understood since Goethe's original work in 1980 and 1981. The universe has to reheat. It's not enough just to make the universe expand. We have to somehow leave the early universe in a state where it's appropriately thermalized, where we've generated the dark matter, where the baryon we've got the right ratio of matter to antimatter, so we can roll into the nuclear synthesis stage moments later. And so this was originally assumed, obviously, to be driven by inefficient quantum processes. If you make those processes too efficient, the vertices will add terms to the effective potential of the inflaton and potentially break the theory that you were trying to create. H is small but not zero. So the field oscillates about its origin, and it looks like a lightly damped oscillator. And you can show without too much trouble that the scale factor in this scenario is going to scale like t to the 2/3. And that scale factor, or that growth, is exactly what you would expect in a scenario where there is no pressure on average. And so what we would think of as a dust or matter-dominated universe. So the field obviously comes out of the inflationary phase with small inhomogeneities that are generated quantum mechanically during the inflationary phase itself. And inflation itself, in that trillionth of a second, lasts maybe 10 to the minus 30 seconds, so a tiny slice of that trillionth of a second. During the next 10 to the 12, 10 to the minus 12 seconds, the universe may grow up to 10 to the 15 times larger. So if the inflationary phase accounts for at least 10 to the 30 worth of growth, this counts for another 10 to the 15. So 10 to the 45, a factor of 10 to the 45 of growth of the universe can happen in this first trillionth of a second after the Big Bang. So at the very end of that scale, we're at LHC energies. So we've got a great deal of growth happening in a very short time, obeying unknown physics. That's the take-home message here. But given an inflationary model, we can say when it ends. We know that we have an almost homogeneous inflaton condensate. That's the job of inflation, to produce that in some sense. We can assume that we have a quadratic minimum because we're expanding about the minimum of an unknown function. And so we wind up with accelerated expansion and obviously a double dot. The time dependence, the second derivative of the scale factor, is less than zero. So if we have matter in bulk that is pressureless, that is in a universe that's dominates a universe that's free to expand, that's actually going to, or you would expect that that would lead to something that would look very much like galaxy formation. In other words, on large scales, you can't resolve the timescale of the sloshing field. This is a somewhat different density perturbation spectrum. You have a short scale cutoff corresponding to modes that left the horizon during inflation, but you're going to get a system that we would think that we understood. But for whatever reason, that picture took a long time to evolve. And so most of the thought that was given to an inhomogeneous early universe from the 1990s onwards focused on the phenomenon of resonance. And so the first people to write on this, people like Brandenburger, Trashin, Stanov, Linde, Kaufman, and Starobinsky. So there was a flowering of papers on this topic in the early 90s. And what they did was they said, well, let's put the spatial derivatives back into the wave equation. So we've taken them out to have inflation. We're going to put them back in to see what happens. We wind up with an expression that's going to look like this. The 1 over a squared just comes from using co-moving coordinates. So as the universe expands, our sense of length changes. The 3h phi dot term we think is subdominant, but it's acting as a mild damping term. And we're going to put in small fluctuations at initial time where we've got our background field phi naught, and we're adding a small fluctuation, and we're going to expand that as an integral over all of its possible Fourier modes. And so we put that in, we get the minus derivative term that we had previously. Wait a minute. The derivative term we had previously is going to turn into a plus k squared thanks to the two factors of I that are picked up by this derivative here. We can split out the phi naught term because that's our background term. And so we wind up with an expression for the time evolution of the perturbations that looks like this, with this term that's going to be given by the second derivative of the potential. And so this is a function of phi naught. Phi naught itself is a function of time. So for every situation other than a quadratic potential, the perfect quadratic potential where the second derivative is just equal to a constant, what we now have is a time-dependent forcing term that is multiplying this particular mode phi k, and of k itself can obviously take any value that we want, any real value that we want to give it. And so what that leads to is that leads to something that looks very much like a Matthew equation. And a Matthew equation is one of these, classical second order differential equations. You don't learn about it right away, but it's sitting there waiting for you. And it has some beautiful properties. One of those properties is that for some values of the B and Q parameter, both constants in the Matthew equation itself, it has exponentially growing solutions in other regions of the parameter space. It has regions that are periodic in time, but often with a short oscillation and a longer modulation imposed on top of it. So this is a very specific case where the pumping term is purely a cosine, but in general, obviously, the second derivative of the field can be something much more complicated. So if we take we can make general arguments about the behavior of these functions using a tool called Floquet theory. And so our general second order equation looks like this, where we're forcing the x of t, multiplying it by some forcing term, whose only real requirement, apart from some very weak continuity and differentiability requirements, is that it's periodic with period t. And given that information, you can show that this equation has two solutions with these both functions of t, and then you multiply it by these so-called Floquet indices. And so the p plus and minus are periodic in time, and the mu k are the Floquet indices. So I'm not going to talk about how to calculate them in detail. The key thing to know about them, or the key piece of information we need to know about them, is that they either come as an imaginary pair, in which case this is just a periodic term, or they're real valued, and they're going to come in a pair where one is they both have the same magnitude, one's positive, one's negative. And so in the real valued case, one of these terms is going to be growing exponentially. And so sometimes you can find the Floquet indices analytically. They're always computable numerically. For the models that we're mostly looking at, the numerical tools are the ones that we need to use to do that. And it turns out, as a matter of practice, the shape or the detailed question of which mode is in resonance and which mode is not in resonance, that depends very much on the detailed form of the potential, or more specifically, its second derivative. And lastly, the a squared under the k squared is coming from the fact that the universe is growing. So if we take the expansion of the universe out of the picture, then the amplitude of the oscillating field would be genuinely constant in time, and the particular value of any given length wouldn't be scaled by the expansion of the universe. So in general, what you have is like a perfect, you solve the Floquet indices, and then you imagine that your particular solution that you're interested in is going to be moving adiabatically through this solution space, so that these parameters in real situations, for at least real situations for people doing inflationary cosmology, will be changing slowly as a function of time. So this is a typical example. This one is, I took this from a paper by Ammon and Losnov. And so what you see is that this particular, these are the regions where the Floquet indices are real valued. Otherwise, the case where they're zero is just the imaginary case where they're both imaginary. And you can see that for different values of k, as the universe expands, different values of k will find themselves either in a region like this, where there's no exponential expansion, or alternatively can find themselves in a region like this, where there's not any exponential expansion, but that they remain in the resonance band for a relatively long period of time as the value of the phi field changes. So this corresponds in some sense that the delta phi k look like the momentum modes of the underlying inflaton field. And so this is something very much like stimulated emission. Once you have a large number of these modes, the occupation number tends to grow exponentially. And so you produce a cascade of modes in a particular momentum state, a very, very highly non-thermal situation for the field to find itself in. The modes move through the resonance bands, phi slowly decreases, and then typically you're going to find yourself in a region where the resonance is relatively weak or is turned off. And so that the resonance starts and then stops. And you also obviously need to make sure that the value of phi itself at the end of inflation is high enough so that the perturbations are able to sample the resonance during the oscillatory phase. So eventually what happens is that this process goes on long enough. And so you started with a very smooth inflationary condensate, which is oscillating backwards and forwards between the two extreme values. And eventually the perturbations grow to the point where that a condensate becomes highly inhomogeneous. And so this video is actually one that I had to hand. It's actually a video for it's one case where we're going to consider two fields. And so the field on the left is the inflaton condensate, and the field on the right is a field that is coupled to the inflaton through a biquadratic coupling, like this one here. We're just going to let it run for a while. And so I've scaled the inflaton field so that this is a spatial slice. It's a single slice through space. And I've scaled it so that the amplitude of the field is always equal to unity. And what you can see is that the perturbations grow substantially in the chi field, and then they back react and they produce similar perturbations in the phi field, even though there's no immediate resonance there. And so you go from a situation where you have a very smooth universe, one of the fields has, it's sitting in essentially a vacuum state. You go to a situation where the apparently homogeneous condensate is fairly rapidly fractured as the universe expands. And this is a set of dynamics that has been studied and discussed since the early 1990s. So the thing that particularly catches my eye about this, or the thing that I've been thinking about since around about 2010, is that entirely separate to the phenomenon of resonance, there are so-called breather modes in nonlinear field theories, or the nonlinear wave equation. They're topological in the sense that they're not associated with a conserved charge. So you can imagine the solution will melt without having to dispose of any quantum number that it might be carrying. They're akin to classical kink solutions, or the famous propagating tangent profile of the wave that flows down a canal as the lock is open at one end. But these things are more akin to the field jogging on the spot. The field is moving up and down at a single point. It has some typically spherically symmetric profile field, and then there's some oscillation of frequency omega. More often what you see is that the profile itself has some slow modulation, but the period of the profile ideally is much bigger than the period of the fast oscillation of the field, something like 1 over omega, up to factors of pi. So the key condition for the existence of oscillons is the potential has to be subquadratic near its origin. And in other words, it's the field is going to be increasing less rapidly than phi squared. And the easiest way to make that happen is obviously to have the next order, the next leading order term in the Taylor series for a symmetric function. Simply to make that something that is where the phi fourth term has a negative coefficient in front of it. These have been studied by various people since the 1970s. I think the earliest paper is by these two Russians from 1976, but their application to cosmology was something that was considered by Kolb, Marcelo Gleiser, and Ed Copeland, among others. And so the key thing here is that just because these solutions exist, just because you can find a particular quasi-stable solution to a theory that you're interested in. The question is will they actually be populated? Will the early universe, it's going to can potentially go through resonance, can become very inhomogeneous. But are you going to drive the early universe into a state where these oscillants actually exist? And so the interesting thing with that, all that occurred to us, so myself, Mustafa Amin, Raphael Flauger, and others working together in sort of 2010, was that as we noticed that simple inflationary models are increasingly ruled out by data. And so what that did is it told you that because we know that as you squeeze the amplitude of the inflationary perturbation spectrum, the likelihood is that the potential seems to become flatter and flatter in order to meet that observational constraint. So that tells you that the gravitational wave amplitude is low, but it also tells you that viable models are going to scale like phi to the p with p less than 1. Potentially even a tangent profile where the potential is essentially flat at large field values. So you're still typically quadratic at the origin. So that means that the kinds of potentials and simple single field models of inflation without adding any extra complexity that will satisfy that requirement are also the potentials that are most likely to or that are at least able to produce oscillants, not necessarily most likely to. So your typical Taylor series looks something like this. And the investigations of this by Ammon and others actually started with a pure phi-6 potential, with obviously the quartic and quadratic terms present as well. So that potential is entirely unrealistic. It produces a spectral index and a gravitational wave background that's very different from what we see in the sky. But you can solve for the oscillant profile exactly in both 1 and 3D. And this was done by Ammon and Shirokov, and also Ammon working on his own in 2010. The next thing that happened was that working together, we proposed this model of monodromy inflation. And so there was a bunch of people who contributed to this. So the archive paper is there on the archive if you want to go take a look, also in PRL. And so this model has strong resonance. It also has a relatively small gravitational wave background, which looked good in 2011, but may not actually be small enough in 2025. But it's also a well-motivated model. It's a model that people had been looking at for other reasons. I mean, there possibly, a cynic would say that there are no truly well-motivated models of inflation, but this one was derived for other reasons from stringy arguments. We didn't have to create it in order to, produce the effects that we wanted to see. And so naturally, what we found when we did simulations and when we looked at the analysis behind this is that for a sub-Planckian value of this mass term here, it very naturally produced an oscillator-dominated universe. And also, it turns out quite a strong gravitational wave background on gigahertz scales. We'll talk a little bit more about that in a second. And so this suggested, at least to us, and it seems to be something that's holding up, is that oscillant formation is generic in a model where you have strong resonance at the end of inflation and a relatively low value of the that naturally produces a low value of the gravitational wave background. And it does that because you've got to make a fairly sharp transition from what you assume to be a phi squared potential at the origin and something that has the appropriate shape to ensure that the gravitational wave production is relatively suppressed as you get out to large values of phi. So to look at a specific example, this is actually a case for a tangent potential or T-model inflation. And so this is going to start with delta rho over rho of 10 to the minus 5, or the standard inflationary background. And so we can look at a scenario with quite large flock A indices. The previous one, I showed that the flock A indices weren't large, but this one, relative to some appropriately dimensionless set of units, we're seeing a flock A index for modes that move through this region here of pushing upwards towards 20. And so this is a 3D simulation of what happens in this scenario. What I'm plotting is the density as or the density contrast in a slightly funky set of units, but it's really the contrast on the scale here that you're going to watch as the simulation plays out. And so this is passing through resonance. And what we're seeing is we're still seeing like a density contrast on the order of a few. And then suddenly, what we see is this is our wave equation. But suddenly we see that there's density variance across the simulation volume on the order of 50. And you can see, and these ones that are kind enough to sit on the walls, you can see that inside of these things, we're looking at 25, 30, 40, 50. And actually in this particular simulation, the peak density is actually about 150 times the average density. But the typical density at any given point is much closer to zero because you've got a handful of regions that are significantly overdense. So there's no gravity in this scenario other than the overall expansion of the universe. There's no local attraction between these things. And these, what we're seeing is the formation of oscillons inside of the very stable configurations of our scalar field. So these are what we sometimes in our own group refer to as wild oscillons. So they interact with the environment and each other. They're not the nice, clean and spherically symmetric objects that we write down from semi-analytic arguments. There's no local gravity, and there's very little theory of the interactions. If you take two identical oscillons and collide them, if you have them in phase or out of phase, you'll either get repulsion or a merger. But once you have complicated oscillons that have different internal phases that aren't naturally in a well-defined state, there's a lot of things going on in the simulations that aren't necessarily well described in semi-analytic treatments of oscillons. And the last thing to say is that their lifetime is unclear. It's unclear how long these things will actually last in the universe, but we do know that they're present in the simulations for several Hubble times. So that while their internal clock is running on the speed of the field, their apparent longevity is much longer than than even hundreds of oscillations of the scalar field about its minimum. So I just want to show one other plot. So we're looking at the moment at with two former students of mine at Auckland and my postdoc, Peter Heyman. We're looking at what happens if you take two oscillons and arrange them so that they get driven towards each other. And so this is now a plot of the field. And so we're seeing the oscillating field is oscillating in place. The energy that's associated with this oscillation is located at a single region of space. And you see that in this particular case, something that looks very much like a merger has taken place. Initially, there was one oscillon that was kind of moving in from the side, almost makes it out to the other side, and then it gets kind of pulled back towards the center. So there's certainly a huge range of dynamics can happen to oscillons that go beyond anyone's, at least certainly that I'm aware of, any semi-analytic treatment of the behaviors of individual oscillons. And that's something that we need to think about in terms of making sense of what happens in the early universe. So the other thing that can happen or will happen in this phase is that we know that resonance produces gravitational waves. So just that the phase of exponential growth of the fields produces fairly naturally a gravitational wave background. And that makes the contents of the universe, lumpy, they're moving quickly. And so they're generating gravitational waves, not in the way that inflation does, because h bar is not equal to zero, but they're generating gravitational waves simply because material is being rapidly accelerated inside of the universe. And so this was worked out by Klebnikov and Kachev in 97. There was a sort of renaissance of this topic. I was one of the people who worked on it in 2006 and 7. But there's essentially three sets of analyses that took a reasonable amount of time to get the codes to agree with each other. So these three sets of people were essentially working contemporaneously or certainly independently on this problem. And so one of the interesting things is that the general resonance background is often at gigahertz scales. So it's at very high energies, very high frequencies. much higher than we would see from LIGO or gravitational wave detectors currently on the drawing board. It's also relatively large for a stochastic background measured in the units that people typically use to keep track of these things. But also in the case of an oscillonic background, you also often find more complex structure than you do if you've just had resonance itself. And it's to do with the formation of these extra structures that live in the model or that live in the universe, once resonance itself is turned off. So I think this is a beautiful topic. I just want to put in a quick plug for it. Anything above 10 kilohertz is probably new physics. The best way we know to make high frequency gravitational waves is orbiting neutron stars. But once you get to a frequency where the neutron stars, can't generate gravitational waves, then there's essentially nothing we know that will produce a strong gravitational wave signal. And so I think there's a strong argument for just building a gravitational wave detector that can see that, because there's a vast range of hypothetical processes in the universe that would potentially produce gravitational waves above 10 kilohertz. And it would be great to go and see if any of these possibilities were there. And so it's obvious that when you build LIGO, when you build the first gravitational wave detector, you go after the most promising and most likely sources, which is neutron star and black hole mergers, from stellar remnants. But potentially, maybe now we're at a point where it's worth thinking about high frequency searches. It's also worth mentioning that those are technically challenging. You can't just take LIGO and put it on a tabletop. But there's some interesting summaries of this, Roshan and White on the archive last year, and also the High Frequency Gravitational Wave Working Group. I hope I've got the right number there. There's a group of people who are thinking about how to develop the detector technology, and they have a recent survey out, which is worth taking a look at. So the last possibility I want to look at during this survey talk is what happens if we put gravity back into the model, and at least to begin with, we take the overdensities that are produced through resonance out of the model. And so I said at the beginning that it's possible we have a universe that's matter dominated. We know that small perturbations, initial perturbations in a matter dominated universe will grow. That's the mechanism that we see producing structure in the universe that we live in today. We believe that primarily the gravitational potential of the dark matter, those initial perturbations grow as a function of time once the universe, once we enter the matter-dominated phase. And so we see structures like this in simulations. We see pictures like this when we take galaxy surveys and plot them appropriately. And we see that this cosmic web, this large-scale structure, we see this arising both in the universe that we observe and also in our simulations of the universe as we think that it is. So it took a long time to see this, a surprisingly long time in some sense. If you go back to quadratic inflation and you say, well, this is pressureless matter, it's well understood physics. We have dark matter in the universe. We know what it does. We don't necessarily know what it is. But that doesn't change things significantly. But in 2010, several people, myself included, looked at what happens if you just take m squared phi squared inflation. You look at the perturbations, you include their local gravity. So in some words, a model that had been written down, I think in 1984. So 26 years later, you're asking, what happens in detail to the perturbations in these scenarios? And so my own work on this was with Raphael Flauger and James Gilmore, who at that time was a PhD student with me at Yale. And we showed that gravitational collapse will happen before reheating. In other words, we showed that reheating, you don't know exactly when it's going to happen in this scenario because it doesn't come with physics that will give you reheating. We just showed that it has plenty of time to happen before reheating must occur at the end of that 10 to the 15 worth of growth that you get in the first trillionth of a second. So it's hard to simulate numerically if you want to do that because there's a fast timescale that corresponds to the movement of the field around the bottom of its potential, which is given essentially by 1 over m. And there's a slow timescale, the Hubble timescale, which is the time it takes for the universe to double in size. And once the universe is 10 to the 5 times bigger, the Hubble timescale is much longer than the oscillation time of the field itself. So the thing that allowed us to go beyond this prediction that collapse would take place, or to do it in an organized way, was to see that we could actually simulate this scenario using the Schrodinger-Poisson limit. So none of the matter in this scenario is moving relativistically. Nothing's been horribly accelerated. Nothing's moving at relativistic speeds. And so in this case, there's a well-known reduction of the Klein-Gordon equation that allows you to make sense of the Klein-Gordon equation essentially as in a Schrodinger limit. So you take the general Newtonian gauge, you write the epsilon, and this, you have to be slightly psychic to do it, maybe for the first time, but you write it in this form here. And you make a series of WKB-like approximations. It's very much a similar move. You'd go from the Klein-Gordon equation to the Schrodinger equation itself. And you get an equation that looks like this, that this amplitude here, now just its time derivative is given by something that's, well, you've got this operator here. And then you've got something that that looks very much like the Schrodinger equation, except that the potential here that is controlling the wave function is the potential that's generated by the gravitational field, sorry, of the matter that is represented by psi. And so the amplitude of the wave function, if you're going to interpret it that way, must be much larger than 1. So you have a situation where you have many quanta, and you can imagine, the total amplitude of the wave function is proportional to the density of the universe. And then in an expanding universe, you subtract away the average density in order to get the local response to the gravitational field. And so we realized that we were able to simulate this because we'd already been thinking about the Schrodinger-Poisson equation in the context of ultralight dark matter, a variant theory of dark matter that assumes that the dark matter particle is one that has a very small intrinsic mass. And so this leads to the formation of an ultralight dark matter. You see the formation of solitons. And so these are the ground state of the Schrodinger-Poisson system, that they're collapsed regions where the wave function has become very large but can't collapse any further, essentially because of some quantum pressure that holds them out. And so we see these collapsed regions inside of at the centers of what look otherwise like NFW halos. And so we took the code that we developed to describe ultralight dark matter in the present day universe, and we were able to apply that to the post-inflationary universe. And in that scenario, we could start to evolve the post-inflationary universe and to the point of gravitational collapse and beyond. There's a possibility of primordial black holes. I don't want to say too much about that because I'll be stealing Anne's thunder if I do that. And as I said, this scenario maps to ultralight dark matter, a very mathematically similar proposal, but operating in the present day universe. And so we're going to talk a little bit also about gravitational wave signals. So just to work very quickly through the sort of developments that we've been able to chase down since then. I think that the key thing is to recall that the universe can grow by as much as 10 to the 15 times larger between the end of inflation and reheating. I've used that number a bunch of times during this talk, but the thing to compare it to, or the thing to hold it against, is the fact that the present day matter-dominated phase in the universe corresponds to around 10 to the 4 worth of growth. So this is potentially a much longer matter-dominated phase than the one that produces galaxies in our universe. And eventually that process in our universe gets switched off by the transition to dark energy. Whereas in this case, you've got a matter-dominated phase that can last far longer, produce much richer and more complex structures. So in simple models, delta rho over rho is actually about 10 to the minus 6 at the end of inflation. If you remember that the spectral index is a little bit less than 1. So the small perturbations have the small wavelength perturbations have a smaller amplitude than we see for the perturbations in the microwave background. But that means that we have like 10 to the 9 worth of growth up our sleeve before we have to make sure as theorists that that reheating has taken place in order to thermalize at temperatures, that we don't have to start worrying about doing thermalization at temperatures where we can potentially observe the physics that is associated with that. So this nonlinear phase is potentially much longer than the present one. The universe can reheat quickly if the couplings permit it, and it must thermalize at some point, but it means that we have this potentially very long stage. It's not guaranteed to be there, but the potential for it exists. So I'm just going to go very quickly through the next steps that we have taken at Auckland and with our collaborators at Göttingen. So first thing was simply to point out on largely theoretical grounds that we would expect the formation of inflaton halos, so something like an NFW halo and inflaton stars, the actual solitons, that are seen in ultralight dark matter scenarios and a variety of other things. We drew very heavily on the parallel with fuzzy or ultralight dark matter to make that happen. And we used the Preschecter formalism rather than numerical simulations to predict the growth of overdensities. And indeed, that's pretty much what we saw in a subsequent codes where we actually used, for the first time, an adaptive mesh refinement code which was able to follow the universe into the most overdense to most collapsed regions without having to simulate the full grid with that kind of spatial resolution. And so that was, again, a code that we developed to address problems in the late universe. We were able to apply it to the early universe. So just saying that very briefly, the gravitational soliton, we've taken the time dependence out of the Schrodinger equation, and you find that there's that the profile of the soliton has a single profile with some scaling for the total mass of the soliton and also for the mass of the particle that you're using to make it out of. There's no analytic solution for this. There's a couple of nice semi-analytic approximations, but generic profile is something that you're able to solve for without too much trouble. One of the interesting things about this is that more massive solitons have a smaller radius. The more massive the soliton, the larger its gravitational field. It squeezes itself in. Its density grows higher and higher. And so eventually you will get to a point where the soliton will want to be smaller than its Schwarzschild radius. It either at that point becomes unstable or it forms a black hole. That's a little unclear. But you certainly have a black hole production mechanism sitting inside of this here. The literature on these is spread from mathematics to astrophysics, so there's still a bunch of interesting questions to ask about them. So I'm just going to use my last couple of minutes to go through a couple of the simulations we did. So this is our first one with Benedict Egmar, a PhD student of Jens Niemeyer's. And so this is measured in units of the Hubble length at the end of inflation. And we're seeing gravitationally collapsed objects with a mass of about 20 kg, so maybe a little bit smaller than a Labrador retriever. We went a little bit further. We put in a clever mesh refinement, and we were actually able to see the formation of solitons constructed out of the collapsed inflaton in the early universe, and also seeing something here that looks very much like a cosmic web. We're able then to take, we verified the Preschecter calculations that we'd done, and then we just ran those Preschecter calculations right through to, as late as we could imagine this matter-dominated phase lasting, and we see that, by the time we've had 36 E-folds, so, that's obviously, a larger number than thinking about exponents relative to E rather than relative to 10. And you can see that some of these objects would naturally move into the region where they wanted to produce potentially primordial black holes picked out in this region here. So there is definitely the possibility of primordial black hole formation in these scenarios. So this is our direct numerical comparison, and this is the extrapolation using the validated Preschecter formalism. Another thing that can happen is that, again, in the late stages of that first trillionth of a second, You're moving material around, you're forming massive objects. And so there is the possibility of gravitational wave emission. This particular model is obviously not, we had to choose a particularly extreme set of circumstances to push up into visible regions, but it's also the model that probably has the weakest gravitational wave emission. The very last or the most recent thing that we've done on this was to say, well, what happens if we have resonance and then we allow that to set, we don't necessarily form oscillons, but we allow that resonance to set the initial state of the universe. And so what that does is it takes a universe that was initially inhomogeneous at a level of 10 to the minus 5 or 10 to the minus 6, and it pushes it to a point where it is now the resonance grow, the overdensities grow to be of order 1 in the first couple of e-folds after inflation. And so in this case, we again see the formation of solitons, but we see that happening well before any kind of scalar field collapse would have happened in the purely m squared phi squared model. And so models that undergo resonance and then undergo gravitational collapse have a much richer potential post-inflationary behavior than they would do if we're looking purely at the quadratic case. So just very quickly looking at some consequences and conclusions here. I think it should be obvious to anyone who signed up to this conference, or very quickly become obvious that the early universe can be home to some very complex nonlinear dynamics. If you just take gravity and it's a very simple scalar field, you can form solitons. If you take gravity and a nonlinear scalar field, so one that's potentially forming oscillons, it's actually scenarios that's poorly explored at this point. The nonlinear fields on their own are potentially forming oscillons, which again have their own complex and rich behavior. As gravitational wave generation is definitely going on. So from the oscillons plus resonance, typical inflationary models, we're looking at gigahertz scales. From the solitons that are produced slowly, from the gravitational collapse during this phase, we're looking at potentially actually millihertz is probably an underestimate, but sort of in the hertz to kilohertz frequencies produced late in this epoch. And finally, I haven't talked about it, but this will change the matching between astrophysical scales and the early universe. Again, with potentially observable consequences if you know in particular what your inflationary model might be. So lots of questions to answer. What happens if we put in oscillons and gravity in a long structure formation phase? What are the interactions between wild oscillons? How are they different from the ones that happen in much more idealized cases? What about the gravitational wave generation, both early or late in the matter-dominated phase? Lots of other mechanisms can do this, but what would this signal look like? It's poorly described. Primordial black hole formation, that's going to be covered in Anne's talk. Reheating, we haven't talked at all about couplings to other fields. There's lots of things that can happen there. Dark matter production has to happen somehow during this phase. And also the possibility of phase transitions, which we're hearing about in Riske's talk. So I just want to end on this last slide. It's been a slightly tumultuous time for science, both here in New Zealand and obviously in the United States. And this work has been done in both places and supported by funding agencies in both places. So I just wanted to make, it's always traditional to thank our funders as we end a presentation. But in this case today, the thanks is particularly heartfelt. So thank you for listening, and thank you to those who have supported us, and very much looking forward to the discussions during this online meeting. Thank you.